Okay, so our next example looks a little more intimidating than the first, especially as we have like pulleys everywhere and then this thing here, and then you look at this, you're like, what the heck's going on there? And then I have this mass hanging over here and it's torques, and suddenly everybody kind of panics a little bit. So let's kind of talk this through to make it a little less intimidating. Let's see, what do I have? I have this thing here is a hinge. So what does it allow what's going on inside the picture to do? Well, it's hinged here. So if I have too much of a torque applied in the counterclockwise position, this thing will rotate up, and too much of a torque applied in the clockwise position, it'll rotate it down. And then this thing, what you're told is we want to determine the tension on this cable that's hinged or that's attached to this board. And you're told about the cable, that it's a frictionless cylinder. I'm sorry, that it's frictionless. And what that means, remember from our previous sections, is that, let's see, this line here then is massless over this frictionless thing. That's our way of saying it's not contributing. It's just holding things up. And that because this is frictionless, then we know that the tension on this side is going to be exactly the same as the tension on that side. So let's go ahead and do this thing. So I have a force of tension coming up like this, and a force of tension going directly up that line. So these things haven't changed. We're defining those things exactly the way as we have before. The one thing you aren't given is the mass of this beam. So here's the thing with this, is that if you aren't given the mass of it, then we're not going to worry about its center of mass to pull down. There's no way that you can figure that out if you aren't provided that, given all of the other variables. So the question wants to know, what is the tension? So we want the force of tension. And we want to know the force component, the force X and the force Y on the hinge A. So I look at this, I'm like, okay, so these tensions, these two are the same, but the force acting over here from the X and the Y from what's going on out here, well, gosh, that there, that's not going to be the same as these tensions. So that means I have too many variables. So I have to attack this in two different ways. So I do need to use torque, and then my suggestion would be to use forces. It's just probably going to be easier that way. So what I'm going to do, instead of writing it all out in terms of counterclockwise and clockwise, is I'm going to do what we're used to, is that our force is up. I'm going to call it positive. My force of tension from this thing, even though we're using the sine theta, just think of it in terms of we want the y components. And I'm given an angle that this is 63 degrees. So I want the y component of that. Well, that is the FR sine theta. So it's this force of tension pulling there times this 10 meters times the sine of that. So that would be my two ups. So the sum of my forces in the y, if I will, or let's just take it straight to the torques, the sum of my torques. What do we have? Up is positive, so I have this force of tension, r sine theta, so at 5 meters. And then I have plus a force of tension at 10 meters. And this one is sine 63. Sine 63. Now again, we're not including the mass of the bar because we're not given it, so we're not worrying about its center of mass. But I am given that there's this 80 Newton thing just randomly hanging out there, because why not? Why not? So that one's going down. So minus this 80 newtons, and that's at 13 meters. And what's that all equal? If this thing is static, all of that equals 0. So I can rewrite this. I'm going to factor this force of tension out. So I pull that out, that leaves me with a 5 meters here. And then let's see, what else do I have? I have plus, then these pieces here, 10 meters times sine of 63. Moving that 80 times that 13 meters to the other side equals 80 times 13. So now I've solved for my force of tension. So that is this 80 times 13, there we go, divided by 5 plus 10 sine 63. Beautiful. Let's see what we get here. Oh, I wasn't nice to myself. Normally I crunch this out ahead of time. So 80 times 13 divided by 5 plus 10 times sine 63. Now here's a note to you. When we just did rotational motion, all of our angles were in radians. So if you get a weird answer, what first thing you want to do is check to make sure that you're back in degrees. So let's see. And that gives me, whoa, that is not the right answer. There we go. That makes sense. 74.77 newtons. Cool. So now we have that. Let's see. So the sum of our forces, those things, well, that's just the exact same thing as we've been doing before. And now we've defined what these forces are, right? We just have an X and Y component from this hinge thing that's new to us. But I can just refer to that as the force in the X and the force in the Y of this. It doesn't even matter that I can't figure out what that angle is, because once I set that equal to all of the X pieces and all of the Y pieces, that gives me that force in the X and then the force in the Y. So let's see how that looks. So the sum of my forces, let's go with the X one, because if you realize something, you should look at this and say, okay, I have this force in the X coming from that piece of tension. Everything else is in the Y, right? So if all I had was that and nothing counteracting that, well, this thing would be accelerating that way. So there must be a force, sorry, Skittles. There must be a force going this way. I'm sorry, a force counteracting the pull from this going that way. And that's going to be the X component of that A. It's otherwise known as the normal. So let's see. I have, if I go that way as positive, that will give me the force in the A and the X of A minus the force of tension times cosine of 63 equals 0 for this to stay static. So now I can just move this thing over to the other side. I already know what the force of tension is, so I can throw that in there. And I say that A in the X, so the force of A in the X is going to give me this 74.77 times cosine of 63. That's it. So now for the sum of forces, let me do a different color. Sum of forces in the Y, well, there's a few more pieces, but we're just going to do the exact same thing, right? So I have this thing down, and if I'm calling this out and I'm kind of looking around that thing, then that would be the force in my Y. So my A in the Y plus force of tension plus force of tension sine theta. And we're doing forces, not torques, so I don't need a distance. Then minus 80 newtons equals 0. Known value, known value. So my A in the Y is going to be 80 newtons minus this force of tension. I want to factor that out. No, I'll leave it like that. Minus the force of tension sine theta. Put in the numbers. 80 newtons minus this 74.77 minus 74.77 times sine 63. Let's see what we get. And I get a number that then kind of scares me, and I think, oh my gosh, I've done something wrong. So I get AY equals negative 61 point what? 4. So what does that negative mean? What assumption did I make over here? The assumption I made is that I'm looking at this like upward force. So if this comes out negative, what this is saying is that at equilibrium, for all of these forces to balance, this force must be going in the downward direction. So I've talked to you about this before with trying to figure out what the direction of acceleration is or the direction friction is acting. And what I've said before is that if you make an original assumption on something and you end up being wrong, the way you figure out that direction is by doing the math. Because this force should be positive. I've defined positive, should be positive if it were up. I came up with a negative number. So that negative number means that this component of the force is going down. So let's take that piece out and say this is how we know this is going down. This one, well, that tension is going up, this is going in, so this force is indeed going this way, right? Because that's how those are counteracting each other. That'd be like the normal force. That's the contact force between the two. So that tells me that we're looking at the hinge action. The force of the hinge is actually happening downwards for that piece. So yay, there you go.